Okay, we're going to see a couple applications of solving systems of equations. The first one will be about finding parabolas. If you have three nonlinear points on the plane, then there is exactly one parabola that is going to go through those 3 points. So, so here's the first example. I'm going to show you how to do this with an example. Find the parabola that passes through the points 1, 7, 2, 15, and negative 1, 21. Okay, so if you put them in order, this would be first because this input is to the farthest left. Then so negative 1, 1, 2, so we go from 21 down to 7 up to 15, which means these 3 points are not on a straight line. Um, I don't plan to give you any problems where the 3 points are on a straight line because that would be misleading. There wouldn't be an answer for that. There wouldn't be a parabola. What we would end up doing is finding the straight line that goes through the 3 points. So the process would work. It's just that we're not going to end up with a parabola. We're going to end up with a straight line if the 3 points were on a straight line, but they're not. They're not on a straight line. So we want to find. So this is the problem. Period. How do we go about solving it? Well, let's assume the parabola is assume the answer is y equals ax squared plus bx plus c. So we want to find a, b, and c. So that makes up the parabola, and this parabola will go through those 3 points nicely. And we want to find out what parabola that is, which means finding the coefficients. If we know the coefficients, we know the parabola. If we know the parabola, we can find the coefficients, as we're going to do right now. So this is the same thing as just f of x. Sometimes we will call this f of x, sometimes we'll call it y. So if we plug in 1 and 7 into this equation, we're going to end up with a true statement. The y value is 7, so 7 is equal to 1 squared, so that would be a, times 1 squared, so that's just a. B would be 1. Rather, x is 1 also, because we're plugging in 1, 7. So we have b, and then c is just c. If we plug in, let me go next with negative 1. If we plug in negative 1 for x, then we have 7. No, I don't know why I put 7. It is 21. 21 is the output. 21 is equal to negative 1 squared times a, but negative 1 squared is 1, so 1 times a is a. And then the input is negative 1, so we plug negative 1 for x, and that would be negative 1 times b, negative b minus b plus c. There's no x with the c, so the c is always going to be the same. And then if we plug in 2 into this equation, we have that 15 is equal to 2 squared times a, for a, 2b plus 2b, again, plus c. So we have a system of equations of 3 unknowns, a, b, and c, and 3 equations. We typically put the constants on the other side of the system of equations. I just wrote the constants on the left because that's how the original equation looks like. All right, so now we can solve this by using matrices, the Gauss-Jordan elimination method, which is a really nice method to use. But I'm tempted to just, if we add those two equations together, the b's go away. So we end up with, well, let's do it. Although it is very tempting to use the Gauss-Jordan elimination, which we will probably use in a future video anyway, the method I mean. So it's not a bad idea to review it, but let's just solve this. So I'm going to label this as equation 1, equation 2, equation 3. So, and remember, if we use the Gauss-Jordan elimination method, essentially 6 steps will get us to the complete answer. Hmm. Hmm. Why? Hmm. Why don't we just do that? So let me draw the um, um, the augmented matrix for the system. So 1A, 1B, 1C translates into 1, 1, 1. The constant 7 is going to go next. And then 1, negative 1, 1, 1, negative 1, 1, and then 21, and then 4, 2, 1, 4, 2, 1, and then 15. So there is our augmented matrix. And then we're going to perform elementary row operations to this augmented matrix to obtain a solution. So we can eliminate this 1 and this 1 and this 4 by subtracting um, appropriate factors of this row. So let's take the second row and subtract the first row. That means that the first row is not going to be changed. So we're going to have still 1, 1, 1, 7, 1, 1, 1, 7, and then 1 minus 1, 0, negative 1 minus 1, negative 2, 1 minus 1, 0, 21 minus 7, 14. Okay, that actually works quite nicely. And then we can eliminate this 4 by subtracting from the third row 4 times the first row. So 4 minus 4, 0, 2 minus 4, negative 2, 1 minus 4, negative 3, 15 minus 28, because remember, we're subtracting 4 times as much as the first row. So 15 minus 28 is negative 13. Okay, so we got the first column neatly as 1, 0, 0. Next, we want to convert that into a 1. So we divide by negative 2. So multiply negative 1 over 2, the second row. And that's going to cause us to have 1, 1, 1, 7, 0, 1, 0, negative 7. Still 0, negative 2, negative 3, negative 13. That step, by the way, it was very tempting for me to simply add this to this row to this row, because then that clears this up right away. So sometimes we can deviate from the systematic way in which we are reducing our matrix, and it will work fine. However, I think there is value in being very disciplined and going systematically from left to right, hitting the diagonal elements, making them 1, 1, and so forth. Then that's a little more systematic than just randomly start get rid of things. Yeah, it is very tempting to do that though. All right, so we have 2 steps. So it should take no more than 4 more steps to finish. So I'm going to subtract. We want to clear this 1. make it a 0 and clear that. And we're going to do that in one step. So we're going to take the first row and subtract the second row. And it's a good thing that we have 0 here, because that's not going to change this neat 1 that we already have in there. 1, 1 minus 1, 0, 1 minus 0, 1, 7 minus negative 7, 14. Second row stays as is, because that's the one we are using to eliminate things. And then we're going to add 2 of those onto the third row. So the third row, we're going to add to it 2 of the second row. So 2 zeros plus 0, 0. 2 ones plus negative 2, 0. 2 zeros plus that, still that. 2 of those, negative 14, plus negative 13, that is 27. And that is going to be negative 27. Okay. We can divide the third row by negative 3. Negative 1/3 times the third row. And we will have 1, 0, 1, 14, 0, 1, 0, negative 7, 0, 0, 1, 9. Okay. So far we've done 1, 2, 3, 4 steps. He said 6 steps. Why is it so? Oh, because we did not have to do the first one. Yeah, it is nice when we have a 1 on the upper left corner, because then that saves us 1 step. We don't have to convert that into a 1. That's already a 1, so that saved us 1 step. Otherwise, it would have been 6 steps. We're going to finish in 4 steps. So step 1 is to make this column nice. Step 2 is to get this 1. So now we got 2 1s. So step 1 in this case, because we didn't have to convert this into a 1. It is already a 1, so that's nice. Step 2 is to make this, well, no, that was step 2, I guess. And then we make this a diagonal, or we start extending the diagonal of 1s. And then we wipe off elements above and below this 1. And now we have a nice diagonal all the way down of 1s. And now we need to wipe off non-zero elements above it. But this is already 0, so we don't have to work with that. The only thing we have to do is eliminate that 1 using this 1. So we're going to continue in our work on the next page. We're going to subtract from the first row the third row. So 1 minus 0, 1, 0 minus 0, 0, 1 minus 1, 0, 14 minus 9, 5. And then we have 0, 1, 0, negative 7, 0, 0, 1, 9. Now, what that means is that A is equal to 5, because this is the column corresponding to the A's. Remember, we were writing the columns A, B's, and C's. So apparently A equals 5, B equals negative 7, and C equals 9. 1A, 1B, 1C. And apparently, our solution will be y equals 5x squared minus 7x plus 9. Okay, but now it is a good idea to double check our solution. Plug in the same numbers we started with. So if we plug in 1, we better get 7 out. So this notation means y of 1. It doesn't mean y times 1. It means y of 1, because y is a function of x. So please be aware of this notation. This is y of 1. That's what we mean by that. And that means 5 1 squared minus 7 times 1 plus 9. So that is going to be, of course, 5 minus 7 plus 9. 5 minus 7 is negative 2 plus 9, 7. And it checks because the 0.17 is one of the given ones, 1, 7. Okay, we should check all of them. 2, 2, so 5, 2 squared minus 7 times 2 plus 9. That's going to be 20 minus 14, 6 plus 9, 15. I go back and look. Yep, 215. That checks. Y of negative 1 is 5 times negative 1 squared minus 7 times negative 1 plus 9. Now, here you got to watch out because there's more negatives. So, this is going to be really 5. I'm going to write this in one more step. And then we got a double negative situation. So that is plus 14 plus 9. That is 23, 28. I'm a little nervous because I don't remember. Whoa. No, it should be 21 or 28. Where did I go wrong with this? Let me see. Negative 1 squared minus 7 times negative 1 plus 9. Oh, I don't know why I put a 14. 7. Yeah. So 5 and 7 is 12 plus 9 is 21. You're probably screaming at the videos like, hey, you put a 14 there. Yeah. Okay. So that means that we solved the problem. Here is the parabola. So we were given 3 points. And as long as those 3 points are not collinear, so on the same line, then we can always find the parabola that goes through those 3 points. Now, I'm picking nice points. Sometimes, if you just pick random points, some of the coefficients are going to be fractions, not very nice fractions. And that's okay. Sometimes that is the way it goes. So example 2. Let's say we are given 3 other points, negative 3, 17, 3, 17, and 2, 2. Okay, and the question is find the parabola through those points, through these points. By this, I mean those 3. Okay. So as we did in the previous example, y equals ax squared plus bx plus c. That's a generic, the most general parabola we can ever have that opens either up or down will have this equation. And we're assuming the parabola opens up or down. Okay, and by the way, those points are not collinear because negative 3, if you go in order from the inputs, negative 3, then 2, then 3, we go from 17 down to 2, up to 17, so there is some kind of a V shape. And so that means there is a parabola that goes through the points. So if we plug in negative 3, we are going to end up with 17. Okay, so in the previous example, I put the 17 first. I'm going to put the 17 last because might just as well use the augmented matrix corresponding to the system of equations. So we're going to put the 17 last. We're going to put negative 3 into x. So that's going to be negative 3 quantity squared, which is going to be 9. So 9a, negative 3 times b is negative 3b plus c equals 17. Then we're going to do the same thing with this 3. 9a plus 3b plus c equals 17 as well. and then 2. Now remember, we're plugging into this equation. So 2 squared is 4, 4a. We don't know the value of a, plus 2b plus c equals the output is 2. Okay. So the augmented matrix will be, I want to optimize space. So I'm going to put the augmented matrix here next to the system of equations. So we're going to have 9, -3, 1, 17. So this is the augmented matrix. 9, +3, 1, 17 again, 4, 2, 1, 2. Some people put a dotted line in between so that we can tell those are the coefficients of the variables while those are the constants. As long as we make it clear from the beginning we have the augmented matrix, then I don't see the need for that. But I can see why it is valuable to do that. Now, our first task is to multiply by 1. Rather, not to multiply by 1, to put a 1 here. That should be our first task. However, looking at these numbers, if we divide by 9, we're going to end up with fractions: 1/3, 1 9, 17 nines. -1/3 I meant here, because then the 3 and the 9 simplify down to 1/3. And I'm thinking it would be nice not to do that, because if we just subtract this from this, that's going to give us 0. Well, here, if we subtract the second row minus the first row, we're going to end up with zeros here, here, and here. So we can hold on to put in the 1. Let's do that. So I'm not going to I'm going to deviate from the Gauss-Jordan elimination, because the Gauss-Jordan elimination, strictly speaking, goes in from ones, 1 and then 0, 0 very neatly, and then 0, 1, 0, and then 0, 0, 1, as we go from left to right. I'm going to deviate from that. And I'm going to try to put zeros in as many places as possible first. So we're going to do row 2 minus row 1. And hopefully, so instead of having ones, we're going to put zeros. Okay. So row 2. So the first row is going to stay as is: 9, -3, 1, 17. And then 9 minus 9, 0. 3 minus -3, 6. 1 minus 1, 0. 17 minus 17, 0. And then that's it. So what I achieved by doing this is getting a 0. So none of those elements were zeros. And actually, we don't care whether those are 0, but at this point, what we care is whether any of those 9 elements is 0. Right now, we went from 9 non-zero elements to 7 non-zero elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. None of those is 0. And now 1, 2, 3, 4, 5, 6, 7 are non-zero. And usually having more zeros causes the system to be more easily solvable, or it is easier to solve the system the more zeros we have as coefficients. So now I'm going to divide by 6. So mind, I'm completely deviating from the Gauss-Jordan elimination. This is not the Gauss-Jordan elimination. I'm using row operations to change the matrix into a simpler matrix. Typically, a matrix with more zeros is simpler. So 1/6 times row 2, 9, -3, 1, 17, 0, 1, 0, 0, 4, 2, 1, 2. Okay. And even though we don't have a 1 here, I'm being a little naughty. I'm being a little I'm rebellious. I'm a little rebel right now because I'm going away from the Gauss-Jordan elimination. Yeah, yeah. So this is the you are witnessing the wild side of me by not following the rules, the system strictly. Um, so so yeah, yeah. So row one, we're gonna add, because now the next thing I want to do is, since I already got a 1 here, and again, I'm going against the standard uh, of going from left to right. So this is non not following the rules strictly. So 0 plus 9, and but I'm making sure that there's a 0 here. However, well, I guess it didn't matter because what I'm trying to do is get a 0 here. Again, within reason, the more zeros we have, the better. So I'm going to add 3 of those rows into here, and that's going to create a 0 there. So we're going to have 9, 0, 1, 17. Okay, and then this stays as is, 0, 1, 0, 0. And we're going to take away 2 of the second rows from the third row to eliminate this 2. So we're gonna have 4 minus 0, 4, 2 minus 2, 0, 1 minus 0, 1, 2 minus 0, 2. Now remember, what I'm doing is not following Gauss-Jordan elimination because I'm trying to use fractions as little as possible. Now, I'm not saying fractions are not good. I'm not saying that. What I'm saying is, if I'm doing this by hand without a computer, I rather avoid the fractions. Now, I noticed that if we subtract a 1, well, subtract the last row from the first row, then we're going to get rid of this 1. So we're going to create a 0 here. So we had 7 zeros in the previous step. Now we got, what I meant to say is this. Let me just tell you. So the original system had no zeros in it. Now we got 2 in this step. We still have 2, but I was getting ready to get rid of more non-zero elements. Now we got 4 zeros. If we subtract this row minus this row, we can create a 0 here. Now, the zeros here don't matter. So we're going to do row 1 minus row 3. And we're going to end up with 9 minus 4, 5, 0 minus 0, 0, 1 minus 1, 0, 17 minus 2, 15, 0, 1, 0, 0, 4, 0, 1, 4, 0, 1, 2. Okay. But now notice that if we divide by 5, we can get this to be 1, having a nice diagonal of 1s. Okay, so 1 over 5 times the first row will be 1, 0, 0, 3, 0, 1, 0, 0, 4, 0, 1, 2. At that point, we can finally get rid of this 4 by subtracting row 3 minus 4 times row 1. Notice that we have zeros in this row, so that's not going to affect this So if you do not use the Gauss-Jordan elimination method strictly, the way I'm doing it, I'm just kind of using different elementary row operations to have as many zeros as possible. That's okay. In fact, you should try it out. And if you start realizing, oh, I got a zero here, but that created another number there, that's okay. That's part of the process. What that means is that we're still learning how to do this in an orderly fashion. So the first two rows are the way they are: 3, 0, 1, 0, 0. 4 minus 4 is 0. 0 minus 0, 0. 1 minus 4, 0 is 1. 2 minus 4 of those, 2 minus 12 is negative. 2 minus 12 is negative 10. So accordingly, we should have, so A is 3, B is 0, C is negative 10. So our function is y equals 3x squared plus 0x minus 10. 3, 0, 10. As our final answer, if you're writing this on paper, we omit this guy, so we just write down 3x squared minus 10. So that is our final answer. Now, before we box it, we got to make sure that it fulfills the requirements. It is a little bit more of time, but it does guarantee you earn all the points for this question if this question shows up on a test. Okay, so I'm going to plug in 3, actually negative 3 first. That's going to give us 9 times 3, 27. Now, when we square the negative 3, we end up with positive 9. So 27 minus 10 equals 17. And that checks. I still remember the 17. Now, if we plug in 3, same thing. 9 times 3 is 27, minus 10, 17. We're good. And then if we plug in the 2, we better get back 2. So 3 times 2 squared, that's 12. 12 minus 10 equals 2. So that checks. Okay. So now we can go back and say, yes, this is the correct answer. And that is the way to check that we got the correct answer. Let's do a third example. So 3, find parabola through the points negative 1, 8, 0, 0, positive 1, negative 6. Okay, so negative. You don't have to necessarily do this because if those 3 points were in a perfect straight line, then there's no parabola that goes through them. So I always check, but I don't think you necessarily have to check. Yeah, negative 1, 8. So the slope from here to here is going down by 8 over 1. So the slope is negative 8. The slope between this and this, it's still negative, but it is negative 6 because it goes down by 6. So the slope is negative 8 here, from here to here. The slope from here to here is negative 6. So the slopes are not the same. Yeah, so the 3 points are kind of like this, steep, and then not as steep. So there's a parabola that is going to go through those 3 points. What is the parabola? We don't know, and that's exactly what the problem is about. So as before, we're going to assume y equals ax squared plus bx plus c is the answer. This is called the analytical method because we're assuming there is an answer, and then we have to draw conclusions about how the answer looks like by using the given data. Now, if we were to plug the -1, of course, we will have -1 times, well, -1 squared times a, so that is a minus b plus c, uh, a minus b plus c. And the 8, as written on this equation, would have to go on the left, but I'm putting the y value on the right side equals 8 because then that's the way we typically write the system of equations. We typically put the constants on the right. If you put them on the left, I don't think that is a big deal either, as long as you remember those are the constants that have to go on the right side of the augmented matrix. 0, whoa, 0 makes this way, way nicer because that means 0a, which is 0, plus 0b, which is 0, plus c is equal to 0. So no a, no b, c is equal to 0. And then if we plug in 1, a plus b plus c is equal to -6. Now, the whole point of using matrices is to solve a reasonably difficult system of equations. This system of equations is not that difficult. It is an easy one. Um, yeah, yeah. So in mathematics, we use different tools depending on the size of the problem. Um, you know, it's like if you're making a hole in the ground and it's only 1 foot deep, do we need to hire a backhoe, that is going to excavate the hole? That's overkill, correct? A shovel will do. If we're going to make a hole that is very deep, I don't know, 15 feet or so, I don't know, then yeah, doing it with a shovel is too much work. Then you want to bring heavy machinery. So in mathematics, we have different tools such as matrices. Matrices are great, but if the problem is very simple, that's a big machinery for a very small problem, for a small job. Yeah. For instance, C is already 0. We don't have to figure out what C is anymore. Uh, this is already given here. So we really, knowing this converts the system of equations into, because if we already know that C is 0, that means that A minus B is 8. A minus B is 8 because C is 0. It doesn't add or subtract anything to the equation. And A plus B is -6. If we add those two equations the way they are, then 2A no B is equal to 2, which means that A comma is equal to 1. And if A is equal to 1 and C is 0, then B has to be 7. I mean, we don't even have to write it down. We can do this in our heads. Yeah. So wait a minute, 7, -7. Yeah, because if we add it here, we get a negative number. So 1 plus what number gives us -6? That number has to be negative because 1 plus a positive number is not -6. So, and the answer for B has to be -7. And B equals -7. So we're ready to write the answer. A, where is A? A is 1. So we have that y equals x squared. B is -7, so -7x. And then C is 0. So that's the bottom line. Yep, x squared minus 7x. And I'm looking at it. It looks like it is right by plugging numbers in. So if the problem is simple enough, then we don't necessarily have to use matrices to solve it. Okay, now let's change gears. Um, partial fractions, a very, very heavy topic. It's not that heavy for students who see it. Okay, let me back up a little bit. What happens with partial fractions? Partial fractions is that oftentimes students, when they need it quickly. Um, and if you rush through partial fractions, it can be overwhelming. But if you study it now before you may need it later, then it is not so bad anymore. So the problem with partial fractions that I have observed is that when students need it, they usually rush through it because they needed it right away to solve some other kind of a problem. And so it typically goes very quickly. But if we take our time, such as in this video, then it isn't so bad. Before we show you how we're going to do partial fractions, let me tell you what it is about. Let's start by adding two fractions. So this is not quite an example, but just a demonstration. Say we want to add those two fractions, plus 4 over x plus 2. These are fairly simple fractions. They're very, very simple individually. When we consolidate them into one fraction, that fraction is going to be more complicated because it is going to carry the information of those two fractions. So let's go ahead and do it. So this is very much the same way as we add fractions, regular fractions. So the denominator is different. There's nothing in common. So the way we consolidate them is by multiplying by x plus 2 over x plus 2 on the first fraction, while on the second fraction, we multiply by x minus 1 over x minus 1. Okay. So that's going to give us, now they're going to have the same common denominator. We multiply this carefully, so we have 5x plus 10, 5 times 2 is 10, plus 4x minus 4. So we have the common denominator of x minus 1 times x plus 2. Once we have the same denominator, we can add them or subtract them together without any big issues. And then we simplify the numerator. So 5x plus 4x is 9x. 10 minus 4 is 6 over x minus 1, x plus 2. So the reason why I'm showing you or reminding you how to do the addition of fractions is because partial fractions is the reverse. We are going to give you this kind of fraction, and our job will be to come back to those simpler ones. So assume we're just given that, not those two, and we have to figure out how to separate them into simpler fractions. That's going to be our job with partial fractions. Okay. So now we can actually do an example of what we are actually going to do. Let's say, so this is going to be example 4. Let's say we have 7x plus 2 over x plus 1 and 2x plus 1. I'm trying to work out problems that are going to have nice answers. Yeah, I'll talk more about that after we finish. Okay, so our goal is to split this into simpler fractions. Now, if you have simple factors like that, what we try to do is attempt to break this up into a fraction that has x plus 1 in it, in the denominator, with another fraction that has 2x plus 1. But we don't know what the two numbers will be. And that's our job, to figure out what those two numbers are, so that adding those two fractions gives us this fraction. Okay, so we're going to use the analytical method again. Pretend there is a solution, and we got to figure out the conditions or requirements on those elements, A and B. So pretend we do have, oh, before I forget, there's one thing that is necessary in order for us to do partial fractions. The original fraction has to be a proper fraction. Let me write that down, because that is an important note. I'm going to write it here. So note. In order to break up a fraction, a rational expression, really, a fraction, that's better. Yeah, rational expression. We must have a proper fraction. Now, proper fraction is the one where the numerator is smaller than the denominator. With polynomials, remember that smaller means smaller degree. The degree of this polynomial is 1. Oops, degree is 1. Because there's just an x, the highest exponent that shows up in the polynomial is the degree. And you may think, isn't the degree 1 here? No, the degree is 2, because as written, this is not a polynomial yet. We have to FOIL it out, and then we have a polynomial. Well, when we FOIL this out, we will have x times x, and that is going to give us x squared. So here the degree is 2, so we are good. Well, this is not the example, but I just wanted to show you. So this fraction, this rational expression is all right, is okay to be broken up into partial fractions, because the degree of the numerator, just as in the addition I showed you just now, is 1. The degree of this guy is 2 x's multiplying, so the degree is 2. So this is suitable for being broken up as simpler fractions. Okay, let's pretend those fractions do exist. X plus 1 plus b over 2x plus 1. And then we do the same thing we did with the other fraction, multiply this fraction by 2x plus 1 over 2x plus 1, and then multiply this fraction, b over 2x plus 1, by x plus 1 over x plus 1. Okay. And that means that we have 2ax plus, so we're multiplying a with those two. We have to distribute. So we have 2ax, 2ax, or 2x times a, or a times 2x. I'm just rearranging the 2, the a, and the x, plus a, plus, and then we're going to do the same thing with the b. The b is going to multiply with the x and with the 1, bx plus 1. And now the denominator will be those two multiplied together, x plus 1 times 2x plus 1. Okay. So this sum equals this, but this sum we're assuming is equal to that. So we're assuming that those two are the same. And by the way, this is a polynomial on x. Let's consolidate the x's. Just like in the little example I was showing here. Remember how we consolidated the x's here and we ended up with 9x. 5x plus 4x is 9x. And then 10 minus 4 is 6. Well, likewise here, we're going to consolidate the x's. So this is 2a plus b x plus, and then, oh, here there's no 1 because we're multiplying the b. That's a fatal mistake. Don't do that, please. Multiply by b, so we end up with b, a plus b. So this is a constant, and this is a coefficient of x over the same denominator. Okay. So what we have this far is that the original fraction is equal to this fraction. Doesn't fit into the screen too well. Okay. And in particular, the numerator, since the denominators are the same, the numerators have to be the same. If the numerators have to be the same, that means that the coefficients have to match perfectly. See, this is the coefficient of x. That's the coefficient of x. The 7 is the coefficient of x on this numerator. And we're assuming those two fractions are the same. Yeah, technically up here, this is equal to that, which in turn is equal to that. Yeah, so there should be an equal, but I just started it over. But anyway, those two coefficients have to be the same. So 2a plus b should equal 7. 2a plus b should equal 7. And this coefficient of 2 should match this perfectly. A plus b should equal 2. There. Now we have a neat system of two equations with two unknowns. This is very similar to what we did with parabolas. Do we want to use the Gauss-Jordan elimination? Well, as I mentioned earlier, if the problem is simple enough, then Gauss-Jordan almost gets on the way. It's like if I want to just move a little box, you know, from one place to another, do I need to rent a big, truck, a moving truck? If I'm just taking something small, I mean, just to exaggerate the example, if I'm just taking this calculator from this office to another office, that is a couple miles away, I mean, I can just walk with it. I can just put it in my pocket and walk. I don't even have to drive to get to the other place. But if I'm taking a refrigerator from one place to another place, then yeah, I definitely need a pickup truck at least, or something similar to that, so I can move things around. So the vehicle we use varies depending on the situation. We're not going to use a pickup truck. I'm not going to, especially if I don't have a pickup truck and I don't have a pickup truck. I'm not going to rent one just to move a calculator. I mean, I know I'm exaggerating the point. I'm sorry about that, but I'm not going to do that, of course. And so that's kind of how it works here. The Gauss-Jordan elimination is beautiful. It works great. If the problem is big enough, if the problem is way too simple, there's exactly the same coefficient, then it is almost more work to do to invoke the Gauss-Jordan elimination. We can just subtract these two equations. And 2a minus a, b minus b, no b, a equals 5. And if this is 5, plus what number gives us 2? Well, that number has to be -3. So, I mean, there, two steps, and we are done. It would have taken so much longer to, put the matrix, although the matrix would go quickly also. But still, why? So A is 5, B is -3, and that means that let's write down the conclusion down here. Our original problem is 7x plus 2 over x plus 1, 2x plus 1, yep, x plus 1 and 2x plus 1 has to be 5 over x plus 1. Oh, make sure your a's match. Okay, so I wrote down the x plus 1 first and the 2x plus 1 second. If you reverse it and you put a on top of this guy and b on top of the other, no problem. When we write down the answer, the 5 will stay on top of the x plus 1, and the b, which is negative 3 minus 3, 2x plus 1, will be on top of the 2x plus 1. But what I have seen in the past is that students move those two around. Anyway, I don't know what they do, but they end up putting the 5 on top of this guy and the 3 on top of this one. And that's wrong. That's not the same thing. It's going to give us something very different. So make sure the correct coefficient is in the correct fraction. And that's it. Double check. I'm going to check real quick by inspection, just by looking at it. So we end up with 10x, and then we subtract 3x, so that's 7x, that works. And then we have 5 minus 3, yep, that works. So there is the decomposition of this fraction into two simpler fractions. Let's do, hopefully, a couple more examples. This example was actually almost easier than the, that was 4, so now the next example is 5. It was almost easier than the parabola example. 12 x squared minus x minus 3. Oh, this one is going to be more difficult. X times x squared minus 1. This is a classic problem, kind of a problem. Okay, first, check that the polynomials are of the correct size. The polynomial of the numerator is 2. The polynomial of the denominator is 3, because this is 2x's multiplied with another x, we end up with 3x's multiplied together. So we have a proper fraction. The numerator is smaller than the denominator. We're good. Okay. Now, x squared minus 1, as you know, splits into x minus 1, x plus 1. So we have really 3 factors in the denominator. 12 x squared minus x minus 3. By the way, partial fractions can get quite complicated. You know, the denominators could be much more complicated with that. For this video, for purposes of this video, we're going to stick with relatively simple denominators, but they can get much more complicated. We're not going to do that in this video. Okay, so our goal is to split this up into something over x. Each factor will have its own constant. So a for x, b for x minus 1, c for x plus 1. Now, some of you may ask, do they have to be in that order? No, no, no. You can put this one first, this one second, this one last. There's 6 permutations. So any order of them will be okay. However, once you find your a, if you put it wherever it goes, make sure the number that you find for it goes with that denominator. So it doesn't matter where you put the letters, but once you have them there, wherever you put them, the numbers that you find for those letters have to go with the corresponding denominators. Don't change the denominators. Yeah. Okay. So if this is the case, then how do we multiply them? How do we consolidate them back together into one fraction? So our goal is to split this up into 3 fractions. How do I put it back into one fraction? So then we can compare. Well, what we have to do is multiply. So this has an x. It doesn't have an x minus 1 nor an x plus 1. So we have to multiply this fraction with x minus 1 and x plus 1 on the numerator and denominator. So that's going to be a little long. We have a over x times x minus 1 over x minus 1. That way those two can combine. But we need to combine with this guy also. So we multiply with x plus 1 over x plus 1. Then we do the same thing with the second fraction. We need to multiply with x over x times, we need this and an x plus 1. X plus 1 over x plus 1. And that way the denominator will have all three. See, x minus 1, x plus 1. X minus 1, x plus 1. C over x plus 1 has x plus 1 in the denominator. We need to multiply by x over x and x minus 1 over x minus 1. This is going to take a little bit of work, but, you just do it. So this is a over x times x squared. When we multiply those two, we end up with x squared minus 1. You FOIL x squared minus 1. The denominator, we want to keep it as x minus 1, x plus 1 to clearly show that we have three factors together. Plus b over x minus 1. And then when we multiply those two, we get x squared plus x over x times x plus 1 plus c over x plus 1. And then when we multiply those numerators together, we get x squared minus x over x times x minus 1. Okay, now we have, well, no, we have to distribute the a into those two, the b into those two, the c into those two. So this is equal to, but now we can put it all together in one big fraction with the same denominator, x minus 1, x plus 1. Because we have x minus 1, x plus 1, x minus 1, x plus 1, x minus 1, x plus 1. All three in the same denominators, or a common denominator. So we have ax squared minus a plus bx squared plus bx plus cx squared minus cx. Don't forget to multiply with every term. One of the things I almost messed up here, actually I did mess it up initially, remember? I put bx plus 1. No, it should be plus b, and then I fixed it. Okay. It is, in my opinion, I think it's a good idea to point out mistakes, because I separate the mistake from the person. That's my opinion. So making a mistake doesn't mean there's something wrong with us. Not doing something about the mistake is what can be judged as not a good thing. But making the mistake, as long as we repair it, fix it, just means that we're human. So I'm consolidating the x squareds. This one has an x squared, this one has an x squared, and so does this one. So we have a plus b plus c. All of them have x squared. I'm going to put a little hat on top of those so I know I already used them. Who has an x? This one. So I just scan across. And this one. So we can consolidate those two plus quantity b minus c x. Who's left? Who doesn't have any x at all? So that one and that one are already taken. Minus b, rather minus a. Okay, so we have something x squared plus something x plus something. Well, it is minus something, but that is that something. Okay, the original problem had 12x squared minus x minus 3. 12x squared minus x minus 3. Remember, because I cannot fit it into this screen. So 12 x squared minus x minus 3. That means, and that has to be equal to this. So this has to be 12 x squared minus x. So that has to be minus 1 minus 3. Again, 12 x squared minus 1x. So minus 1x minus 3. 12x squared minus x minus 3. 12x squared minus 1x minus 3. Okay, let's write that down. So a plus b plus c has to be 12. 12x squared minus x. Well, that means that b minus c has to be negative 1 to create the minus x effect. And minus a has to be minus 3. I'm using the same coefficients as the original problem. 12, negative 1, negative 3. So we have a system of equations, 3 unknowns, a, b, c, and 3 equations. Do we use the Gauss-Jordan elimination? We could, but I think that's overkill in this case. A is 3, so okay, so a is 3 because we can simply multiply by negative 1. Okay, so if a is 3, we can plug into this equation. So 3 plus b plus c equals 12, but then we can subtract the 3 from both sides of the equation. So b plus c has to be 9. All right, so b plus c equals 9. But then b minus c equals negative 1. So when we add those two equations, 2b equals 8. So b equals 4. Okay, so 4 minus what number gives you negative 1? Well, that has to be 5. So c is 5. Okay, so our equation 12 x squared minus x minus 3 over x times x squared minus 1 may be rewritten as, okay, the way I set it up, the a is under the x, and a is 3, so the 3 goes on top of the x. None of the numbers is negative, okay. The way I wrote it down, the b is over the x minus 1 plus 4 over x minus 1. The way I wrote it down, the c is over x plus 1 plus 5 over x plus 1. So there we have it. We broke this fairly complicated fraction into 3 simpler fractions. And sometimes we want to consolidate into 1. Sometimes we want to break up into pieces. It varies. It depends. It really, really depends on the application we are working on. Yeah. The way to double check is to add this together, the way I was explaining how to add fractions together to make sure we end up with this fraction. Is it a lot of work? Yes, it is a lot of work, but that will guarantee that we have the correct answer. That is one way to guarantee we have the correct answer. Let's do one more example. Actually, I had 2 more to do. Let's do this one. What example was this one we just finished? 5? Apparently so. So 6. Example 6. Negative 9x plus 22 over, oh, I see why this example is different. 2x squared plus 3x minus 2. Okay, so this is a good example in the sense that the polynomial on the numerator is smaller than the polynomial in the denominator. That's very clear. So that is a requirement for us to start working on partial fractions. If that is not the case, we cannot do partial fractions. We can still break the fraction into simpler pieces. What is required is long division first. But I'm not going to get into that. We just want to work with problems that are doable, easily doable. Well, the other one is also easily doable, but I'm not going to complicate the problem with that complication. Anyway, this is different because it is not clear what the fractions are, the denominators are, the denominators of the simpler fractions. We have to factor this ourselves. You're probably thinking, must I factor that? Yes. Okay, so we know one of the factors has to have 2x, the other one has to have x. Is this a negative 2? Yep, so I'm thinking negative 2 and positive 1 will do, because then the outer terms gives us negative 4x plus 1x is positive 3, and yeah, that does it. So one complication with this problem is that the denominator is not factored. So if you were to do this, it is your job to figure out how to factor the denominator. All right, that's the first part of the problem. Then the rest is the same. So we want to break this up into a over 2x plus 1 plus b over x minus 2. When we have a problem that is that simply, we know we have to multiply by x minus 2 over x minus 2. So we have a, I'm going to do that at once. So a times x minus 2. So 2x plus 1 over x minus 2 plus b 2x plus 1 over 2x plus 1 and then x minus 2. And then if you're thinking, hey, do I have to put the a on top of the 2x plus 1 and the b on top of the x minus 2? No, 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 no. You know, because the factoring, there's no rule that says which one has to go first. At least I don't know of a rule. So if somebody factored this as x minus 2 times 2x plus 1, and you place the x minus 2 first, that's fine. Just remember, whatever number you get that goes on top of the x minus 2, keep it on x minus 2. Don't switch it. Whatever letter you use, that's going to give you ultimately a number. Regardless of what letter you use, you're going to get the same number. So just make sure you keep that number on top of where it's supposed to go. So my a is on top of the 2x minus plus 1. My b is on top of the x minus 2. But if you have them backwards, that's fine. Okay, so now we can consolidate. So ax, well, I better not skip steps. So ax minus 2a plus 2bx plus b over the same denominator, 2x plus 1, x minus 2. And now we can combine. So we have a plus 2b. Those are the x, a plus 2b, plus negative 2a plus b over the same denominator of 2x plus 1 times x minus 2. Okay. So we have something x plus something x plus something x plus something x plus something. Well, that means that those two have to match a plus 2b. So something x, negative 9, plus something, negative 2a plus b, equals 22. Okay, so now we got a system of equations. Can we use elimination? Yes. Can we use Gauss-Jordan elimination? Yes. I'm thinking if I want to use something else instead. Can we use substitution? Boy, do you remember substitution? Substitution seems, let's do substitution just for the fun of it. This equation can be rewritten as b equals 2a plus 22, which we can put into this equation now. So a plus 2 of those equals 9. A plus 2 of those, 2a plus 22 equals 9. And now we can solve this equation for a. A plus 4a plus 44 equals 9. That means that 5a equals, and I'm going to subtract 44 from both sides of the equation. So that is 35. Oh, negative times -1. Let's put it that way. And that means that a equals -7. The only reason why I wrote this down this way is because I forgot to put the negative in front of the 35, and I didn't want to, just squeeze the negative. So I just multiply by -1, which makes it correct. And b, well, b is 2a plus 22. B is 2 of the ones we just found plus 22. So that is -14. 22 minus 14 is 8. Okay. So the two numbers we're looking for are -7 and 8. Make sure you place them in the correct spot. So -7 over 2x plus 1. Okay, so let's write this down. -9 plus 22 over 2x squared plus 3x minus 2, which is the original problem, may be written as -7 over, now I gotta make sure the a was supposed to go over 2x plus 1, plus 8 over x minus 2. Yep. So there is the decomposition of this big fraction into two simpler fractions. The process of going from here to here, the way we did it, is called partial fractions. 7. One more before we get started. We finish. At least I'm going to get started this problem. Maybe I'll let you finish it on your own. Yeah, this is a little big of a problem. So pretend you got 11x squared minus 42x plus 51 over x minus 1, x minus 2, x minus 3. All right. So the polynomial in the denominator has degree 3. X times x times x eventually will get you to x cubed, while the numerator has degree 2. So this is bottom heavy, and that's good. That means we can perform the breakup of this big fraction into 3 simpler fractions. The 3 simpler fractions are going to be some number over x minus 1 plus some number over x minus 2 plus some number over x minus 3. And our job is to figure out what those three numbers are. Let me just get started. I think I'm going to let you finish this problem. We're going to have a over x minus 1 times. Now we got to multiply those two. X minus 2 over x minus 2, x minus 3 over x minus 3. When we multiply those two together, we're going to end up with x minus 2, x minus 3. But the numerator will be, it is going to be the same, but I'm going to multiply the numerator. So we have x squared minus 5x plus 6. The b fraction is going to be multiplied with x minus 1, x minus 3, because we already have x minus 2. So we include what we don't have. X minus 1 is already there, so we include x minus 2, x minus 3. X minus 2 is already there, so we include x minus 1, x minus 3. When we multiply those together, we end up with x squared minus 4x plus 3. And then c over x minus 3 will have to be multiplied with x minus 2 and x minus 1. I probably should have put x minus 1 first and then x minus 2. And we end up with x squared minus 3x plus 2. Okay. And then you have to distribute the a on the x squared. The b has to be distributed, and the c. And then we have to consolidate the x squareds and the x's and the constants. And then we have to make them equal to the consolidating coefficients in 211, negative 42, and positive 51. So please finish this and share your answers for A, B, C. All right, and with this, we're going to stop this video.